Assalamu alaikum students. Today's topic is going to be about electrical potential, energy, and potential due to point charge. Electric potential energy and potential due to point. It is quite similar to absolute potential energy. So, like gravitational field, every charge has electric field which is theoretically expand to infinity. Let's say if this is an isolated charge, let's say Q, and here is a test charge which is also positive, then this electric field will basically affect radically this charge even if it is at infinity. Consider an isolated charge positive q fixed and in space as shown in figure like this, and it has an electric field around it. If a test charge q is placed at infinity, the force on it to the charge, that is isolated charge q, is going to be 0. So if we place a test charge which is positive at infinity like this, then the force of this charge on the isolated charge will be equal to 0. As the test charge is at infinity, which moves towards, you can say, isolated charge q as a force of repulsion acts on it. So if we move this charge q closer to the isolated charge, basically they both are of the same charges, which is positive, because test charge is considered to be as positive. Now if they are both of the same charges, then they both will repel each other, because we have learned from Coulomb's law that same charges will repel each other and opposite charges will attract each other. So work is required to be done to bring it to point A. That means we have to apply some work on it so that it moves from, let's say, infinity closer to this acceleration charge Q, because it, they both will repel each other. So here we go, and here's the work done on this test charge Q. We brought it to point A. Hence, when the test charge is at point A, it has some amount of electrical potential energy. That means it will experience some force which is produced by this isolated charge Q. The closer the test charge to the charge, isolated charge Q, the higher will be the electrical potential energy. The electric field does not remain constant but varies as the square of the distance from the charge. That means when it was over here, the electric field was approximately equal to 0. But as it was moving closer and closer, so we divided into smaller parts, in such smaller parts that in each of these parts the electric field remains constant. Although these electric fields are not the same, but in this region, the electric field should remain constant, because as we are moving closer, the electric field is increasing. So we will say that in this much part only, the electric field remains constant. Now, this is the formula for the electric field. The equation for electric field density is given as E is equal to 1 over 4 pi epsilon naught Q over R square into unit vector R. Now, how do we get this formula? Now, if we remember the formula or the definition of electric field, it is electric field intensity is equal to force per unit charge. Now, if we remember this formula, we also should remember the formula of Coulomb's law, which was about this force, forces of direction or repulsion. So electrostatic force basically which said that the electrostatic force is directly proportional to the magnitude of the two charges and inversely proportional to the square of the distance between the square of the distance between the two charges. So we can represent it like this: F is directly proportional to Q naught divided by R square, where Q naught is the magnitude of the two charges. They are directly proportional to the electrostatic force, and R square is the distance between the two charges, and we have taken square for it according to the Coulomb's law. So this was Coulomb's law. Not up till now. Let's say one more thing. If we convert this proportionality into equality, then we include a constant of proportionality, which is K. Now, this is the formula for Coulomb's law, which says the electrostatic force is directly proportional to the magnitude of the two charges and inversely proportional to the square of the distance between them. Now, what is K? K we know is a constant value having a value of 9 into 10 to the power 9. You can say Newton meter square divided by Coulomb square. This is the unit of this value K. The formula for this K is equal to 1 over 4 pi epsilon. Let me write it clearly. 4 pi epsilon, where the value of this epsilon is 8.8 into 10 to the power minus 12 Coulomb square divided by Newton meter square. Now, what is this epsilon? This is basically permittivity of free space. Permittivity of free space. That means there is nothing between, or absolute potential, or sorry, absolutely nothing, absolutely vacuum between any two charges, and that much permittivity when one charge basically apply a force on the other one, that is known as permittivity of free space. Keeping all of that in mind, we get the value of E after putting the value of F and Q in the equation. E is equal to F over Q. We get 1 over 4 pi epsilon Q over R square, because E is equal to F over Q. We know the value of F, it is 1 over 4 pi epsilon multiplied by Q. You can say Q naught divided by R square divided by, which is a test charge Q. So this Q and this Q cancel out. What we are left with, E is equal to 4 over pi epsilon multiplied by Q divided by R square, and R unit vector is representing the direction of the electric field. So this is how we get the value of E. Keeping that in mind, in order to keep E constant, the test charge is moved moved infinitesimally small displacement delta R, and the work done in this whole scenario can be calculated by the formula W is equal to Q into V. Q into V, and this is the formula for the work done. Now, in this case, where do we take this formula from? It is equal to V is equal to W over Q. The work done per unit charge is known as electrical potential. Now, if we want to calculate the work done in this case, we can say W is equal to minus Q into V, and it is going to be written as minus Q E delta R cos 180. Because they both are moving in opposite direction, the angle between them is going to be 180 degree. That is why we have written 180. But how do we prove that delta V is equal to delta R into E? Now we have the formula that V is equal to W over Q. That means electrical potential is equal to work done per unit charge. We also know that W is equal to F into D divided by Q. We have all the already the formula of force. It is represented as E into Q divided by Q. So this Q cancel out with this Q. And if the work done is in opposite direction, that means if we apply the force in this direction and the displacement is in this direction, or vice versa, then the angle between these two is going to be represented as cos 180. So this continues over here. Let's say this is cos 180. So we can represent it as V is equal to E into D. If D is very, very small, we can say it is equal to delta R for the change in potential. So we can say, if we have space, let me make space over here, we can say now that delta V is equal to E into delta R cos 180. So it is a negative sign. So we can say E is equal to delta V over delta R, and there's a negative sign because of this cos theta. Now, this negative sign shows that whenever we have two plates and the test charge is moving from a positive to negative, that means along the electric field lines, it will always lose its potential. So this negative sign is showing that. So here's the formula for V. V is equal to E into R cos theta. So we have the value of ER now from the value of delta V. Keeping that in mind, we get W is equal to E delta R. Now let us put this value of E in this equation. What do we get? We'll get W is equal to Q into 1 over 4 pi epsilon naught into Q over R square multiplied by delta R. So let me put it in this way. If we bring the negative sign, we have the negative sign in the above equation, which shows that E and delta R in opposite direction, which shows over here. So this negative sign and this cos 180 will cancel out, so we get a positive sign. Now putting the value of E from equation 1 and equation 2, we have from here, we have the equation 1 and we put delta R with it, with Q, we get the value of W is equal to delta W is equal to 1 over 4 pi epsilon naught into accelerated charge Q and small charge Q, test charge, divided by R square delta R. Let's call this equation equation A. This is a very important equation. W is equal to 4 pi epsilon naught Q, which is accelerated Q small, which is test charge, divided by R square into delta R. Now, we don't know what is the value of this square R. We know that there's an average of this distance between the two charges, but we don't know what is the average between these two charges and what is the displacement between these two charges. So if we want to move it, let's say this point to infinity, or we can say we want it to move to infinity, then we have to divide it into again smaller parts. So what do we do? First of all, we just create smaller parts. So let's take a step-by-step process that we move it from here to a new point, let's say point 1. So the distance from here to here, let's say it's going to be represented as RA, and the distance from here to here is going to be represented by R1. So what is the difference between these two distances, let's say from here to here? So it is going to be represented by delta R, which is equal to, you can say RA minus R1. That means the difference of these two charges. Now, in this case, we have the displacement between the two charges, or we want to move in opposite direction. That means if we consider it to be moving in the opposite direction, that means if one is over here, then it will be A minus R1. So the difference between the 2 points is basically represented as delta R. Keeping that in mind, we have to already also explain the average of the two distance. So how do we represent the average? This was RA. This point was RA, and we move it to a new point, let's say R1, which has the same electric field. So this much displacement from the mean position is represented by the average. So how do we take the average? Average is basically taken as the addition of RA plus R1 divided by the number of components, that is by 2. So this is the second equation which we have, which is very important. We have to keep that in mind as well. Now we have the value of delta W, which is equal to R squared delta R, and we are going to put in the values. So now let's the test charge is at a large distance RA from Q, and we divide the distance between RA and RB into infinitesimal small displacements so that the field intensity over each displacement remains constant. Just like I showed before, we divided into smaller parts. Now we have the two values as we showed in the diagram, that delta R is equal to RA minus R1, and average R is equal to RA plus R1 divided by 2. Now putting the values of R1 in the above equation. Now if we want to put in the value of R1 and we want to find out the value of R1, in this case, let us put in the value of RA in this R1, or we can say put the value of RA in the above equation. So let us put in the value of RA. So if we put the value of RA in this equation, so R will be equal to, instead of RA, we can say delta R plus R1 minus plus R1, sorry, divided by 2. Now, why we have done this and how we have done this? Look at this equation. Delta R is equal to RA minus R1. So from here we can say RA is equal to, taking the negative sign to the other side, it will be delta R plus R1. So this is the value of R1, and that is why I've written RA is equal to delta R plus R1. So this is value of RA. Now let us put this value of RA in this equation over here, right over here. So we have R is equal to RA plus R1. So I'm replacing the red sign, the red color of RA in this equation. We get R is equal to delta R plus R1 plus R1 divided by 2. So these two RA will basically add up with each other. So what do we get? R is equal to delta R plus 2R1 divided by 2. Because the LCM is same, we can separate it. Now we can write it down as R is equal to delta R divided by 2 plus 2R1 divided by 2. So these two will cancel out with each other because they have the different term over here. So what we are left with? We are left with R is equal to delta R divided by 2 plus R1. Now we want to find out the value of R squared, not just R squared. Why? Because we have to put in the values of equation A, which was W is equal to Q over KQ over R square, you can say simply. So R square is squared. So that is why we're taking square over here. So taking square on both sides, we take the square. Let me write down clearly. So R square is equal to delta R divided by 2 plus R1 whole square. And we are applying the formula of A square, sorry, not A square 1, A plus B whole square. So which can be represented as A square plus 2AB plus B square. Now applying the same concept over here, we get R square is equal to A square, which is delta R divided by 2 whole square plus 2AB, or we can say 2 into delta R divided by 2 into R1 plus B square, which is R1 into R1 square. So these two will cancel, but there's much more important things to do. This square part, whenever you convert, let's say 0.1 and take it square, it will be even smaller. So you can neglect this part because it's already very, very small as compared to the whole scenario. And even if we take the square of it, it will become more smaller. So what do we do? Neglecting this term, which is delta R divided by 2 whole square, we have now R square is equal to 2 into delta R divided by 2 R1 plus R1 whole square. We cancel out these two. What we are left with? We are left with r square is equal to delta r into r1 plus r1 square. So replacing delta r, which we have over here, putting the value of delta r again in this equation, what do we get? We get delta r is equal to ra minus r1. So putting this value, we get r square is equal to ra minus r1 into r1 plus r1 whole square. So we have to multiply r1 with this one, ra, and with this one as well, with r1. What we are left with? We get r square is equal to ra into r1 minus r1 into r1 plus r1 square. So these two r1 will multiply each other, they will be square as well. So we have r square is equal to ra r1 minus r1 square plus r1 square. So this is in negative, this one is in positive, these two will cancel. What we are left with? Let them cancel out, and we are left with r square. Now we have the value of r square, and we are going to put this value in equation A, which is was of work. So r square is equal to ra into r1. Let's call this equation B, which we are going to put in equation A. So at the beginning of the first displacement, E varies as 1 over RA square plus, and at the end of E varies 1 over R1 square. Since the average is 1 over R square over each small decimal, therefore we can write down as 1 over R square is equal to 1 over R. Therefore, one R is replaced by RA and the other one by R1. So we can write down in the equation 1 over R square is equal to 1 over RA R1. So now let us calculate the work from equation A. Work done in small displacements. We put the value of 1 over r square is equal to 1 over ra into r1, and the value of delta r is equal to, as we know, ra minus r1. We get, this is equation A. We remember this one. So delta w is equal to 1 over 4 pi epsilon q capital Q small q divided by r square into delta r. So we have the value of delta r over here, and we have the value of r square as well. So let us put this value in this equation. What do we get from here? By dividing, we get the work done from r1 to ra is going to be q over 4 pi epsilon naught q's. That means one is isolated charge, the other one is test charge, over 4 pi epsilon naught, and we put the value of delta r, which is equal to ra minus r1, and r square is equal to ra r1, and we can solve them separately by taking the LCM. We get ra divided by ra r1 minus ra r1 divided by ra r1 is equal to 1 over r1 minus 1 over ra. So how do we get this one? We can cancel out these one. So ra cancel out with ra, r1 cancel out with r1. So what we are left with? We are left with 1 over r1 minus 1 over ra, replacing this whole thing with this term. We get similarly in the second displacement, which is going to be from 1 to 2. First it was from a to 1, now it is going to be from 1 to 2, and then it is going to be from 2 to 3, and so on. The work done is in that case can be represented as, in the first case, from 1 to 2, a to 1 was written as 1 over q 1 over over 4 pi epsilon 1 over r1 minus 1 over ra. In the next equation, we can say from 1 to 2, work done will be r1 to 2 is going to be q into q divided by 4 pi epsilon 1 over r2 minus 1 over r1. And similarly, we can move on to q 4 pi epsilon naught if we want to write down the work done from r2 to R3, then it will be isolated q test of q divided by 4 pi epsilon naught into R3 minus R2, and so on till the nth number. So the total work done in moving the charge from Q to point A to B. Now we have considered that this is a test you isolated charge actually, which is Q, and we have to move from point A to point B, which is over here. Now in keeping so, we have done work done from A to 1, let's say work done from A to 1, then from 1 to 2, then 3, 4, until nth, and then from n to b, we have to do the work. So this is the equation from n to b, the last one. So the work done is going to be the similar manner. So work done from Rnth to Rb is going to be isolated charge Q into test charge Q divided by 4 pi epsilon naught, 1 over Rb minus 1 over R1. So let us gather up all the work done which we have done from moving from point A to point B. The work done from moving test charge from infinity to distance R from Q is represented all the values from A to B. We add them all. So we have taken common because isolated charge Q is same in all of those. And the test charge is same as well. 4 pi epsilon naught is also constant, so we have taken common. So what we are left with in the case of terms, so it is minus 1 over r1 plus 1 over r1 minus 1 over r1 plus over r2 minus 1 over r2 plus 1 over r3 minus 1 over r3 and so on till nth. The value at the end it is going to be rb, 1 over r. So as you can see, one is plus and one is minus. So all the terms in between are going to be cancelled out like this. So only two terms are left behind, 1 over r a and 1 over r b. So, so the work done from ra to rb is going to be the isolated charge q, which was this one, the test charge small q divided by 4 pi epsilon naught 1 over r b minus 1 over r a. So if we take the point A to infinity, what will happen then? If we take the point to infinity, what will happen to this work done or potential, you can say energy in this case. So let us put in the value of Ra equal to infinity. So 1 over infinity is going to be 0. So what we are left with? We are left with only this equation that work done from Ra to B is going to be Q small q divided by 4 pi epsilon 1 over rb, or generalized in writing it down in the form of potential energy at point r from q, generally writing it down. So it will be written as electrical potential energy u is equal to q divided by 4 pi epsilon 1 over r, and this is the energy part, but we have to find the electrical potential. So as we remember that V is equal to W over Q, or change in potential energy over Q. So let us divide this whole equation by Q and get the potential electric potential. So the electrical potential at the distance R from Q is written as V is equal to W over Q. We divided by Q. This, if we divide it by Q, this Q and this Q will cancel, and we get 1 over 4 pi epsilon isolated Q divided by R. This is the formula for electric potential at point due to a point. I hope you enjoyed today's derivation, because I certainly did. Inshallah, we'll meet again. Bye bye.